Hello, welcome to another Dante heat treatment simulation tutorial. In this video, I will be demonstrating how to build a 3D press quench model. Before we build the stress model, we will need to build a thermal model in order to generate a temperature history for the part. The temperature history will be imported as a load for the stress model to drive the thermal expansion and phase transformations so that we can see the stress and distortion results and the effect the die tooling has on the part. The first thing we are going to do is set up our working directory. So the working directory I'm going to be using is this temp directory here. So I'm going to open that up, open up command prompt, copy my directory path, change it inside my CMD, and open up Abaqus CAE. So once I have Abaqus CAE open, I'm going to select standard/explicit model, change the model name here. I'm going to be calling this press quench _ T, just to make it easier to keep track in case I have multiple models inside my model tree. And before we actually create a part, I'm going to save the CAE file. I'll call this press quench model and click OK. Since we are only building the thermal model here, the only part we have to create is the 3D ring slice and not the actual die geometries that go along with it. This is because we're going to be modeling the heat transfer from the part to the quench and heat and air cool, and not the heat loss to the actual die. So for the 3D ring geometry, I'm going to be selecting create part. The name I'm going to give it is just ring _ slice. Make sure 3D, deformable, solid, and revolution are selected here, and we can click continue. So for the geometry of the part, we're going to be having an ID of 25 millimeters, an OD of 50 millimeters, and a height of 50 millimeters. So to create the actual geometry, I can select create lines and give the coordinates for the four corners of the rectangle. So the bottom left corner will be 25, 0. The top left corner will be 25, 50. The top right corner here will be 50, 50. And the bottom right corner will be 50, 0. So next we can close up this rectangle, deselect the create lines option, and click done. Since this is a 3D part, we do have to give an angle of revolution. And assuming uniform boundary conditions here along the circumference of the part, we don't actually have to model the full ring slice, only a slice of the model. So for the angle, I'm going to be giving it 5 degrees, and we can click OK. So now that we have the part created, we can go to the assembly module and create an instance of the part. So the assembly module is basically an environment in which you can add multiple parts to. So this environment is where you will be applying the boundary conditions, constraints, or interactions for the model. So now that we added the part to the assembly module, we have to mesh the actual part now. So inside module here, we can click mesh, make sure part is selected, and here we have to create the mesh for the part. So for any Dante model, it's typically a good practice to have finer elements along the surface here so that we can capture the carbon gradient for a carburizing model, or the thermal gradient for a thermal model in this case. So the easiest way to do that for a ring slice model is to select seed edges and select the 4 edges that make up each inner rectangle surface here. So using shift, I can select the 4 edges on this rectangle. I'm going to rotate the part, hold shift, and select the 4 edges on the other inner surface rectangle. So now that we have the 8 edges selected, we can click done, and this local seeds window will pop up. So once this window pops up, underneath bias, we can select double, and this will allow us to change the minimum and maximum size of our seeds. The minimum size that we're going to be using in this case will be 0.2, and the maximum we can change from 5 to 2, just because our part is a little bit smaller. So next we can click apply and take a look at the seeds here. So you'll notice based on the direction of the arrows, our seeds are actually decreasing in size towards the corners, the vertices of the part here, which is what we want. If your part, however, your arrows are pointing in the opposite direction, all you would have to do is flip the bias here to change the direction in which the seeds will grow or shrink. So if our arrows are pointing in the wrong direction and we click apply, you'll notice that our elements in the middle of the edge here are smaller than the elements, the seeds near the surface of the edge, which will be the opposite effect of what we want. So to fix that, we can click flip bias, click the select button here, select the edge that we want to flip the arrows for, and click done. So now that we have point 2 and 2 defined and our arrows are pointing in the right direction, we can click apply, close out of this window, and click mesh part. So if you use the value of 0.2 and 2 for the minimum and maximum size, we should have 6,435 elements here. The last thing we have to do inside the mesh module is go to mesh and change the element type for this part. So by default, the element type is on 3D stress, but since we're building a thermal model here, we want to use heat transfer elements. So if we scroll down to the H, we can select heat transfer and click OK. Once we've changed the element type, the next step for building a Dante model is to create our different sets that we will use to apply the materials, the initial condition, and the boundary conditions. So to do that, the first set that we're going to create will be inside our part module, and this will be the all element set. So to create the all element set, we can go to Tools, Set Manager, click Create, and type all elements. We can leave either geometry selected or use element option here, but either way we can click continue and box select the entire part. So the purpose of the all element set is this is the set that we're going to be applying our material to. Since for this model we only have one part with one material, we only need to define one set here. So once we have the all element set defined, we can go to the assembly module and we are going to be creating our nodal and surface sets. So to do that, we can go to Tools again, Set Manager, and the first set we're going to be creating is our all nodes set. So again, we can click Create, type all nodes, and in this instance, we're going to be selecting the node option instead of the geometry option. So click Continue, and box select the entire part, same as before. We can click Done, and our all node set is created. So the all node set is the set that we're going to be applying our initial conditions to. So the initial conditions for this model will be the initial temperature, the phase transformation kinetics, and the base carbon of the material. The next set that we're going to be creating is the monitor node set. So to do that, we can click Create, Monitor, Node, select Node, and choose any arbitrary node on the surface of the part. The monitor node set will output the temperature history or the temperature value at that specific node as the analysis is running. This is a good way to double check the results while the analysis is running instead of having to wait for the final results at the end of the analysis. In case for a larger model that may take hours to run, this is a good way to double check. So with those two node sets created, we can click Dismiss and create our surface set. So to create our surface set, we can go back to Tools and go to Surface here and open up the Surface Manager. For a thermal model, in this case, we only have to create one surface set, and this is the exposed surface. So for this part, since this is a slice, all we have to do is select the 4 exposed surfaces of the ring slice here. So the top surface, the OD, the bottom, and the ID surface. So this surface is where we will be applying our HTC values to simulate the heat transfer that is happening during the heating, the press quench, and the air cool step. So now that we have the exposed surface set created, we can dismiss and open up the Dante Model Builder from the plugin tab. Next, since we haven't actually defined the type of Dante model it is yet, we can go to Model Type, select Thermal, and click Create Dante Model. So this will tell our Dante Model Builder plugin that this will be a thermal model. And before we actually move on to the other tabs, let's save the model first. So now that we have the active model set as pressquench_t and thermal, we can move on to the materials tab. So for the materials tab, we can select the all elements set that we created inside our part module as the part element set here, and select the material that you want to use. For this particular model, I'm just going to use the S10XX material and click Add Material section. If the material is added successfully, in the model tree here, you should see a material added underneath the materials dropdown. So the steel S10XX material, a section created, so basically the all element set that we defined, and inside the part here, the section assignment, so assigning the material to the all element set here. So after we define the material, we can move on to the steps tab. And the first thing that we're going to do before defining any steps is select the monitor node. For this particular model, we're going to be having a heating step, an add load step, a press quench step, or move load step, and an air cool step. So the first step is the heating step. For the previous step, we can select initial, and for heating, we can just leave the value as 3600 seconds or 1 hour. Let's create the step here. And next, let's define our second step. So the second step will be the add load step. The previous step will be heating. And for the add load step, I'm going to be using a time period of 1 second to add the load. So again, we can create the step and move on to our third step, the press quench step. So for the press quench step, our previous step will be the add load step, and the period I will be using 1000 seconds. Click create step. And our fourth step is the remove load step here. The previous step will be press quench. And similar to the add load step, the time period we're going to be using is 1 second for the remove load. We can click create step. And last but not least, our air cool step. For the air cool step, our time period can be 7200 seconds or 2 hours, just to make sure our part fully cools down to room temperature. So click create step. And after we define the 5 steps here, we can move on to the initial/boundary conditions tab. The first thing we're going to do is click add initial condition/predefined field. And this will give us the option to change the or to edit the initial temperature of our model. So we can leave the field as step here as initial, and the field type will be temperature, and this will be applied to the all node set that we defined. So the initial temperature that we want the part to be at before the analysis runs is 20 degrees Celsius. So we can type 20 here and click apply. The next option is the phase transformation kinetics, which we can leave as default. So for this particular material, the default value takes the value from our material database, and I believe for this particular material, the default value is -4, which means that our austenitizing type will be rate dependent, and our tempering and volume change by carburizing or nitriding will both be inactive. So we can leave this as default and click apply, and move on to our total carbon weight fraction. So our total carbon weight fraction, which is the base carbon of the material, we will use a value of 0.002 to model 1020 material for this particular model. So we can click apply, and those are the only 3 initial conditions that we have to define for this thermal model here. So we can click X, and if we define those correctly, if we look inside our model tree here and scroll down to predefined fields, you'll notice that we have 3 new predefined fields defined or updated inside our model tree. So the first one is the kinetics mode, which we use default, which has a value of -4. Our temperature, our initial temperature for the model, which is 20 degrees, and our base carbon of 0.002. So now that we define our initial conditions, we have to apply our HTC values as the boundary conditions. So instead of manually defining the HTC values, we can import the generic values from our DANTE database. So the first HTC value I'm going to be importing is our furnace HTC. So if I right-click the table, click read from file, go to my DANTE database here, inside our 61A folder, Abaqus link, and inside our generic HTC data, I can select generic furnace heating here. So once I click OK, I can remove the first 3 lines here and click apply. The next HTC value will be the oil quench. So same thing as before, if I right click the table, click read from file, open up the folder here and select oil quench, click OK, and remove the first 3 lines, same as before. So I'll click apply, and the last HTC value we have to define is our air cool HTC. Right click, click read from file, open, and select air cool. Remove the first 3 lines, click apply, and we can close out of this window here. So now that we have our 3 HTC values defined here, as you can see the interaction properties in our model tree, we can go to add interaction to apply the HTC to the specific surface for the specific step that we want it to be for. So the first step is the heating step. So we want to select furnace, and we can use a constant ambient temperature of 950 degrees. So if we click apply, that applies this HTC to the exposed surface set for the heating step. Next is the add load step. So for the add load step, we can consider this as a transfer step. So transferring from the furnace to the actual press quench. So for this step here, we can use our air cool HTC, and instead of an ambient temperature of 20 degrees, which would be way too low, we can use a temperature of 400 degrees Celsius to represent the radiation of the part to the immediate surrounding environment. So for this, we can click apply and move on to our press quench step. So for press quench, we're going to be using our oil HTC, and this will have a constant ambient temperature of 50 degrees. Click apply and remove load. So for the remove load step, I'm going to be using the same variables here, so the oil quench HTC and the ambient temperature of 50. Lastly, for the air cool step, I'm going to change the HTC to air cool and use 20 degrees to represent room temperature. So next, I'll close out of this window and save my model. So that was everything we had to define inside our Dante model builder. If we go back to the models tab here, all we have to do now is submit our job. So if we give this a second here, inside our message window, our model is currently pre-processing, and as you can see here, we've successfully pre-processed our model, and our job monitoring output is now available. So this means that our .sta file, or the status file, has been generated inside our working directory here, which is a good sign, which means our model is currently running. So if we open this file up, you'll notice that the first line here is the steps, and if we take a look at the very last column here, this is the degree of freedom monitor. So for a Dante thermal model, this outputs the temperature at the monitor node that we defined. So for step 1, increment 1, you'll notice our degree of freedom is 20.3, which makes sense since we defined an initial temperature of 20 degrees Celsius. If we scroll down here, maybe if I reload the file, end of step 1, so end of our heating step, our temperature is basically 950 degrees. So next, step 2 is our add load step, which is only 1 second long. And here you'll notice our temperatures start to decrease, so basically transferring from our furnace to the press quench equipment. And inside step 3 here is our actual oil quench. So our temperature starts to drop drastically, and the oil quench step, or when you have a quench step inside a Dante model, this step usually takes the longest just because of the high temperature gradient. So the 50 degrees versus the 950 degrees surface temperature of our part due to the heating step. So if we give this maybe a minute to run, this should be done in maybe 30 seconds to a minute time. So if we go back to our Abaqus CAE, we can go to the visualization tab here and open up our ODB file so we can take a look at the contour as the model is running. So first we can change to plot contours here, and let me just orient this part. And to look at the temperature here, this is the NT11 variable. So right now we're in the press quench step right here. If I select frame selector and go back to the very beginning, we can go through each increment here to see the temperature of the part. So first we're in the heating step right now. You'll notice that our part is starting to heat up. Our temperature here is starting to increase, especially at the corners here, just due to geometrical effects. And if we keep on scrolling through each increment, you'll notice our time right now, it's the end of the heating step. And our part, the lowest temperature is 949. It's basically a uniform 950 degrees value, which is what we define for our constant ambient temperature for the heating step. Okay, so our press quench model has now finished running, or our thermal model, I mean. And if we go through each increment, maybe take a look at the add load step here, you'll notice our temperatures start to decrease. And now that we're into the quench step, at the end we should be around 50 degrees. Next is our remove load and our air cool step. So since this is a thermal model only, we don't get to see the stress and distortion. That will be in the next video. But some of the variables that we can look at, some of the DANTE variables that we can look at is the hardness here. So since we didn't include the carburizing model here, our hardness, especially on the surface here, is pretty low. We can take a look at the different volume fractions here. So we don't really have any retained austenite for this particular material and process. We can take a look at the ferrite, lower bainite, martensite, pearlite, tempered martensite, which is 0 because we don't have tempering active based on our phase transformation kinetics that we used. And last but not least, upper bainite. So now that this model is finished running, we can take this temperature history from this ODB file and import it into the stress model that we're going to be building next video. Thank you for watching this video. In the next video, we're going to be importing the temperature history from this thermal model that we just built into the stress model in order to see the stress and distortion due to the press quench equipment. If you guys have any questions, you can visit our website at www.dante-solutions.com or email us at support@dante-solutions.com. Thank you.